Hey Calc students, in this video we're going to go over continuity. I have one example that involves multiple points of continuity and discontinuity, and in it we're going to be covering the definition of continuity, how to prove a function is continuous at a point, and also how to properly write out cited vertical asymptote limits when it's going to positive or negative infinity, and also how to prove a function has a jump discontinuity. Okay, so to prove a function is continuous, you gotta show three things. You have to show the function limit at the point x equals a in my bullet points over here. You have to show that the limit of f at x equals a exists. How do you do that? You gotta show that it equals a real number. Sometimes you can just do it directly by direct substitution. Sometimes you need to show the left and right limits exist separately first and then conclude that the two-sided limit exists. Now I say two-sided limit, that's to be clear. When you say the limit exists, that means the two-sided, but you have to state that. You have to be clear about that. I'll show you. You also need to show, the bullet point number 2 there on the definition of continuity is you have to show that f of a is defined. In other words, you need to show that it equals a real number. You also must state the conclusion, number 3, that the limit you got in part 1 equals the function value you got in part 2, and you need to state that equation explicitly. Okay, in the process, we're going to cover the bottom 2 bullet points of VA limits and proving a certain discontinuity is a jump. Okay, let's do it. I created this example here. Okay, so first, find the value of k, which makes this function continuous at x equals -1. Okay. For this to be continuous, at -1, this is the breakpoint for -1, the left limit will be the limit of this, needs to equal the right limit. And then we can solve for k. Okay. All right, so first thing is first. We would need the limit as x goes to -1 of f of x to equal the limit as x goes to negative. So this is from the left. We need to evaluate the limit as x goes to -1 from the left, which would be this piece. Let's actually work that out, and then we'll set it equal to the other in the second step. So this is going to -1 of what? X plus 3. It's important you use limit notation when you're doing a problem like this. This is calculus, so we use calculus notation, not pre-calc. Notice I showed what piece I'm using. That proves to me you know which piece of the function is to the left of -1. Now this is a polynomial, so we can do direct substitution. We get what? -1 plus 3, and that of course equals 2. Now we'll do the right limit. Limit as x goes to -1 from the right of f of x equals what? The limit as x goes to -1 from the right of, it is -x plus k. So what is that? It is -1 plus k, which is 1 plus k. Now, a little side work. We need 2 to equal 1 plus k. So we need k to equal 1. Okay? So then I can come back up here and think, okay, so k equals 1. I've got k equals 1. And now I just need to prove that it is continuous at x equals -1 for that specific k. Let's do that. So now, in red, I will prove that f is continuous at x equals -1. Well, I've actually already shown the left limit equals 2. I don't need to do that again. And I've shown the right limit equals 1 plus k. So it would be helpful to write the limit as x goes to -1 from the right of f of x equals 1 plus k. But what is that? It's 1 plus -1, which equals Oh, excuse me, not -1. I knew I was making a mistake there. K is +1. Oops. 1 plus K, well, that's 1 plus 1, which is 2. Okay, so notice we've got the left limit equaling to 2. We've got the right limit equal to 2. We need to state that the limit of the whole function is 2. Since the limit as x goes to -1 from the left of f of x equals the limit as x goes to -1 from the right of f of x, and since both of those equal 2, then the limit as x goes to -1, two-sided, not just one-sided, of f of x equals 2. This is proof of the bullet point you see below me in the PowerPoint there. I've just proven that, number one, I've proven the limit exists at a. In this case, the limit exists at -1. Well, do you notice nowhere above I've actually said what f of -1 is? So I need to state that. What is f of -1? Well, f of -1 gets plugged into this one. So f of -1 is -1 plus k. K is 1. So it's 1 plus 1 equals 2. This is step 2 below me. I'm not done. I need to do 3. 3 is this. The limit as x goes to -1 of f of x equals f of -1. This is the most crucial conclusion that you must have exactly like that. Notice my limit is not sided. It's not a left limit or right limit. It's just the limit as x goes to -1, the total limit from both sides. Now I can conclude. It's fine, like on a test, you can just write, therefore, f is continuous at x equals -1. That is a sufficient way of writing quickly on a test when you're time crunched. That's sufficient for writing up that it's continuous. Okay, we have done the first part. We have shown that the value of k that makes it continuous, and we proved it. Okay, now let's show that f is not continuous at x equals 1 and 2, and we'll actually go further than that. We'll classify the types of discontinuity. Okay, at x equals 2. Let me move all this work a little bit to the side. Okay, at x equals 2, we are, at x equals 1, let's do that first. At x equals 1, we are here on this break. So we're looking at this from the left and this from the right. I'll work in green. What is the limit as x goes to 1 from the left of f of x? Well, that is the limit as x goes to 1 from the left of -x plus k, but we know that k is 1 because we already found that, so it's this. Well, what's that? That is negative, plug in 1, negative, plug in 1, we can do direct substitution, plus 1 equals 0. Okay, fantastic. That's the left limit. Now we got to check and see what's happening with the right limit. What is the limit as x goes to 1 from the right of f of x? Okay, well, let's see. What is that piece? Okay, that piece is this rational function. So that would be the limit as x goes to 1 from the right of -1 over x minus 1. Now, I can already see that this is going to give me a finite number in the numerator, -1, over 0. Don't just write this, and don't just say dne. Now, it is true that this is approaching 1 over 0, informally. It is true that this limit will not exist. But remember, when we're doing a one-sided limit at a vertical asymptote, and what I wrote here is showing this is a vertical asymptote. When we were writing a one-sided limit at a vertical asymptote, you need to state which infinity it goes to. So don't do what I just wrote here. Instead, instead, here is a quick way that is valid for you to write to show your work. What is this equal to? It's negative 1 over 0, but which side is it approaching 0? If x is approaching 1 from the right, then the x values as it gets closer are a little more than 1. If I have a little more than 1, 1 plus, minus 1, then these differences are positive. So the denominator is approaching 0 from the positive side. It's approaching 0 from the right. So what is happening here? The numerator is a fixed finite negative number. The denominator is always positive, but approaching 0. So this is going to negative infinity. This is a compact way of writing up your work to make it very clear that this is a VA. It's a vertical asymptote. And on the right-hand side, it's diving to negative infinity. Okay. So if there was a question, it said, show that there's a vertical asymptote at x equals 1, that would suffice. You just need to show one side goes to either positive infinity or negative infinity. Now let's classify what kind of a discontinuity is this? Well, if one side goes to a finite number and the other side goes to infinity, this is an infinite discontinuity. In fact, if either side goes to plus or minus infinity, you only need one out of the two. If one out of the two or two out of the two go to positive or negative infinity, then this is an infinite discontinuity. So f has an infinite discontinuity. At x equals 1. That is a fancy way of saying a vertical asymptote. It has a vertical asymptote. Okay. All right. Last one. I'll work in purple. Okay. Purple. We're going to look at what about at x equals 2. Now at x equals 2, we are here and here. I can see that x equals 2 is in the domain. Okay. So let's do the left and right limits. Let's do the limit as x goes to 2 of f of x from the left. And that is the limit as x goes to 2 from the left of negative 1 over x minus 1. Well, this is actually direct substitution because 2 is in the domain. So I can just direct substitute, and I get negative 1 over 1, negative 1. Great. What's the right limit at 2? The limit as x goes to 2 from the right of the original function. Well, what is that? That is the limit as x goes to 2 from the right of this cosine thing of what? Negative cosine of pi x minus 1 plus 1. I'm going to put this in parentheses to clarify it's the limit of that whole thing. So I just copied it. And cosine is continuous for all real numbers. So since it's continuous on its entire domain, it's continuous for all real numbers. Hence, you can just do direct substitution to evaluate this limit. So I now can drop the limit notation. It's just pi 2 minus 1 plus 1. But what's that? That's negative cosine of pi plus 1. Cosine of pi is negative 1. So this is negative 1 plus 1. And that is 1 plus 1, which equals 2. Notice my chain of argument here. I started with the limit I want to find. I wrote equals the limit on the right-hand side, which I plugged in the appropriate piece of the piecewise function. Once I can do direct substitution, I drop my limit notation. I can plug everything in, do pre-calculus to evaluate it, and I get 2. Okay, now what kind of a discontinuity is this? The left limit is a finite real number, negative 1. The right limit is a finite real number, 2. This is a jump discontinuity because both sides are finite, they exist, and they're different. since a compact way of writing this up could be, since the limit as x goes to 2 from the left of f of x equals -1, which is not equal to 2, which is, but 2 is equal to the limit as x goes to 2 from the right of f of x. Everything I wrote here is true. The key here is this does not equal this. So you could just write this you could just write this, but do not just write that. Don't write since -1 is not equal to 2. I need to see the limit from the left is not equal to the limit from the right, and the above work justifies that they both exist. Okay, I'm just going to undo back to here. Okay, since this is true, then f has a jump discontinuity. At x equals 2. Okay, there we go. There's my examples. Make sure you know the definition of continuity. Make sure you can properly show your limits when you're doing a limit at a vertical asymptote. Make sure you're showing which infinity those sided limits are going to. And this is my feedback on how to compactly write it and show it. This is totally valid way of writing it. Yes, it's true that this is DNE in the sense that the limit doesn't exist, but we write it that way to show which infinity it's going to. Last thing, when you're showing something's a jump, show that sided limits exist, show that they equal real numbers, which is the same thing, and show that the two sides equal different things. And that's enough to show it's a jump. All right, see you in class.